we have to carry on with the organic chemistry. I want to set up like a flowchart. We have alkanes. What reactions did we have with the alkanes? Just to sort of summarize. Here we had, first of all, combustion. Because they are hydrocarbons. Now, the products are carbon dioxide and water vapor. Then the next set of reactions was something called substitution. We could take off something and we could add a different element, one of the halogens, for example. Okay? But it was a substitution reaction. Then we said we can crack an alkane. Okay? And we didn't really go into much of it, but we can polymerize an alkane as well. Okay, cracking and polymerization. If you read up in your textbooks, you will see they refer to something known as reforming. We won't go into reforming, but what they're going to do is they're going to change the shape into whatever one they want. Okay. Now, how do we go from an alkane to an alkene? We crack an alkane. Are you all with me? Then we get the group of compounds known as alkenes. Okay, now alkenes can also undergo combustion because they are hydrocarbons. They do not undergo substitution, they undergo addition reactions. And what can we add? We can add hydrogen, we can add water, and we can add a halogen. Those are the main reactions with the alkenes. Now, I can go and I can go back from an alkane, an alkene, I can go to the alkane by addition of hydrogen. All right? When I add water to an alkane, I get alcohol. All right? The alcohols. The alcohols we had a look at yesterday: methanol, ethanol, propanol. Okay. Now, today, the next step, I can, if I open up a bottle of wine, and I drink half of it, and I leave the bottle of wine standing around open for a week or two. What happens to the wine? It becomes sour. It actually reacts with the oxygen, and that is why when they seal bottles of wine to store for many years, there mustn't be any oxygen in it. Because if there is oxygen in the bottle, the alcohol will oxidize, and it will form something known as a carboxylic acid. Now, first of all, it's an acid. So it has a pH lower than 7. The most commonly known carboxylic acids for you people would be vinegar. Vinegar is a carboxylic acid, and that is what forms when the alcohol in the wine is left to oxidize. It forms vinegar, which is a carboxylic acid. Okay, so how do we recognize carboxylic acids? If I take ethanol, and I allow it to oxidize, I will get a carboxylic acid, and the carboxylic acid will look like this. There is the original part there, and we will get, keep the carbon there, we will get double bond oxygen, OH. There is our carboxylic acid. It's just, it doesn't have to be like that. It doesn't matter. Okay, now that is an indication of a carboxylic acid. Remember, how do I recognize an alcohol? There is a hydroxyl group. Okay? We call this the carboxyl group. We can also write it RCOOH, or without the hyphen. The R is just the rest of the hydrocarbon tail. It's that part. Okay, so that R part can be a carbon and a carbon and a carbon and a carbon with hydrogens on it. You follow? Okay, so sometimes they use R accent. It just means there's a different molecule. Okay, to this one that I had. Now, the carboxylic acids, how do we name them? Well, the ending is something oic acid. What would this thing's name be? The prefix depends on the number of carbons. So I don't have methane, I've got ethane, but I don't have ethane, I have a carboxylic acid. So it becomes ethanoic acid. Okay? What would this one's name be? Say it. Methanoic acid. No. Okay. What would this one be? Yes. Propanoic acid. Butanoic acid. Do you follow? Now, okay, they also don't go much further than methanoic acid and ethanoic acid. All right? So you need to be able to recognize it. All right? They are all acids. In other words, if I add them to water, they ionize. Okay? Now, this thing, I can also write it CH3COOH. Do you remember chuku? Yes, that's vinegar. Okay, can you see where it comes from? CH3, 1, 2, 3 hydrogens. There's my carbon, double bond oxygen, hydroxide group. Okay, now, how does a carboxylic acid ionize? What would that reaction look like? Well, we will have CH3COOH. Now, what happens when acids ionize? For example, if I had hydrochloric acid, I get ions. Okay, now which hydrogens would form the ions? Because I have 4 hydrogens there. No. Unfortunately, it is that one. So what would this thing look like once it's ionized? We have CH3COO plus hydrogen. Yes, it ionizes partially. Now, you haven't done equilibrium reactions, which simply means it doesn't really want to get rid of that hydrogen. It actually wants to stick onto that hydrogen. Okay, it's a weak acid. Okay, so the ionization reaction for the carboxylic acids, it is just this hydrogen on the carboxylic group that ionizes. No, the others remain on the molecule. You mustn't let that confuse you. Yeah, if you go like that, I will draw it like that. There. This is what it looks like. Yeah, it is just an inherent property, and that is what it does. Okay. Are you with me? So the ionization of the carboxylic acid, it is that hydrogen. So if I had propanoic acid, then I would have, well, propanoic acid looks like that. Methane, ethane, propane. OH. So there are my hydrogens. So I would have C2H, 1, 2, 3, 4, 5 COOH. How would the ionization look like? Yes, I will get the hydrogen plus C2H5COO and minus because it's a negative ion. All right, do you follow that? If you struggle to write it in this form out of your head and they want it in that form, just draw the picture quickly in pencil and work from there. All right, it shouldn't be very difficult. Okay, so the organic acids are there on page 138 in your textbooks. They say right at the top of the page, when an alcoholic drink is left around open in the air, it turns rather unpleasant and acidic. This is a natural process caused by bacteria. The alcohol is oxidized. Yes, I think so. Technically it will. It is oxidized. Yes? Yes. Julle moet basic carboxylic acids doen. All right. The acid produced when ethanol is oxidized is called ethanoic acid. Its old name is acetic acid. Its common name is vinegar. The next, acetic acid. The oxidation of ethanol, which bacteria are able to do using air as the oxidizing agent, can also be done in the laboratory using a suitable oxidizing agent like potassium permanganate or potassium dichromate. One of the sections we still have to do is reduction oxidation reactions. It's just a short module, 3 pages. All right, so that connects up there. Then, if you go down one paragraph, the ethanol is heated with some of the oxidizing agent. The mixture is then distilled, and the fraction distills around 118 degrees because the boiling point of ethanoic acid is 118. Okay, the liquid collected will have a strong vinegary smell. Organic acids react in 2 characteristic ways. Like all acids, they will react with alkalis, and they will also react with alcohols. Now we will do the reaction of alcohol in the next period. I don't want to do it now because then you'll be totally confused. Okay, so at this point I will stop.
There's no price like the ShopRite price, which means you'll get low prices on everything you need. Like 4 kilos real good frozen mixed chicken portions for only $154.99 and a 2 kilo bag of nice parboiled rice for just $26.99. The ShopRite price, the price you can trust, always.
Organic chemistry. In the previous period, we've had a look at the carboxylic acids. Just to recap, we said from the alkanes, we can go to alkenes. How do we do that? Cracking of an alkane. Okay. From an alkene, I can go to alcohol by the addition of water in the form of steam, and from an alcohol I can go to a carboxylic acid, and this is by oxidation of the alcohol. Okay, now people, I want to carry on with the carboxylic acids at this point, and the carboxylic acids, they in turn can react with alcohol to form an ester. Okay. I am on page 138, more or less. And then 39 to form the esters. Okay. Now, how does this work? If I have an alcohol, let me do them in different colors. Let's just take propanol, OH. And I am going to take ethanoic acid. I'm just not going to draw the functional group on this side, I'm going to draw it on that side. So, ethanoic acid, OH, there we go. Okay, and now we are going to show how the ester forms. Now, it's a polymerization reaction, okay, where one molecule joins onto another one, but we find that a water molecule or a molecule similar to water is split out as a result of this reaction, or is formed as a result of this reaction. So what happens is that the hydroxyl group on the carboxylic acid and the hydroxyl group with the alcohol, that is where the reaction lies. And we find then that eventually, there. So what do we get? We are going to get that there, okay, my hydrogens. There go my hydrogens. What have I got reacting? So now we are going to get oxygen, carbon, double bond oxygen, carbon, and the 3 hydrogens plus H2O. Yes, of the alcohol. I'm not 100% sure. Okay. Yes. I want to take that away. It's just the other way around. It goes there. In actual, no, it doesn't really matter. It's not really important. Where's delete? There. Okay. It doesn't really matter, because what you eventually show is that we have a carbon, oxygen, carbon, double bond, oxygen. All right? Now, we have to name this compound. So, the name of the compound, I have got methane, ethane, propanol, and I had ethanoic acid. So I will have propyl ethanoate. Okay? Yeah. Well, the propyl part is from the alcohol propane, a propanol. And the ethanoate, ethane, methane, ethanoic acid is from the carboxylic acid. So it's propyl ethanoate. If I had ethanol and ethanoic acid, it would be ethyl ethanoate. Do you with me? If it was methanol, it would be methyl ethanoate. If I had propanoic acid, whatever, propanoate. No. Yeah, you won't do more complicated than that. All right. Okay, so if you look in your textbooks, right at the bottom of page 139, there at the top they have a heading, reaction of ethanoic acid with alcohols. The product that is formed is an ester. Okay? We recognize an ester because it has this so-called ester link. There. Okay, carbon, oxygen, carbon, double bond oxygen. That is the ester link. Now, right at the bottom of your page, page 139, there they have got ethanoic acid plus ethanol, and the product is ethyl ethanoate plus water. Well, yes, that must be H2O. Please fix it. All right. This is a condensation polymerization reaction, or just a condensation reaction because a water molecule is split out from the reaction. Yeah. Sometimes it can be something like sodium hydroxide. The Na just takes the place of one of the hydrogens and the OH group, because water in this form is actually HOH. So it could be sodium hydroxide would react similarly. Do you understand? Where the positive proton, the hydrogen ion, is the sodium ion replaced. Okay. But you will work with water. They won't really do funny, obscure stuff with you. They ask it fairly straightforward. All right. Okay, now, still in your books there on page 139, right at the top on the right-hand side. When ethanoic acid reacts with an alcohol, a substance called an ester is formed. The ester, if it is ethanol and ethanoic acid, is ethyl ethanoate. It has a sweet, fruity smell. People, if you have air fresheners that you spray, they smell like flowers and they smell like pineapples and bananas and all funny stuff. The fruity smells. Those are all esters. Okay. So take note. A sweet, fruity smell is an ester. Esters are very common in nature. The taste and smell of fruit is often caused by an ester. Now, fats and vegetable oils, although they aren't sweet smelling, are also esters. The difference is between the sweet-smelling esters, it's just the length of the chain. Okay, so fats and oils are esters. Any fat and oil contains esters. Yes. The cover tabletop, the laminated tops, is also an ester. It's just the length of the molecule becomes bigger and bigger and bigger. Okay. So, they say the solvent for removing nail varnish is an ester. It's got a sweet-smelling smell, ne? Yeah, nail polish remover is an ester. We can compare the reaction of ethanoic acid with an alkali and with an alcohol. If we look at the equations, they are very similar. The big difference between them is that the reaction with alkali is an ionic reaction and the one with alcohol is covalent. So ethanoic acid with an alkali will give me a salt plus water. I just want to show you that. If I have ethanoic acid, methane, ethane, ethanoic acid. Yes. Why do you think I'm reading it? It's one of those obscure stuff that they want you to know. But it's just there. It says the one reaction is ionic and the other one is covalent. It's the third paragraph from the top of page 139. We can compare the reaction of ethanoic acid with an alkali and with alcohol. Okay, I'm going to do the alkali. Name an alkali. Yes, sodium hydroxide. So what is the reaction going to be? Well, the sodium is going to stick there and the hydrogen is going to go there. Ah, wow. So it is going to be like that, double bond oxygen. Now, we have that there. If the proton has broken off in an acid-base reaction, that thing is negative. The acid is ionized. Okay? So that is negative there. And this thing is sodium is positive, so this sodium will go there. So what is the bond? Ionic bond. Say again? Yes, well, it's just, this part is negative. They say the reaction forms an ionic compound. Why is it ionic? Because positive and negative. I have an ion here, and I have an ion there. If I have sodium ions and chloride ions, I have an ionic compound. Now my ion is just very big. Coulomb forces. Attraction between positive and negative. Just like those are stuck onto each other. Yeah, well, be careful. The oxygen is bonded onto that part of the molecule. So the Na just goes there. No, you don't have to. No, it does. There's one is open there and there's the other one. Have a look. Look there. Remember I said acids ionize. What happens when they ionize? It forms an ion. It gives off a proton. That proton. Do you understand? Okay. Have you got it, Johannes? Oh. Okay, so this is an ionic compound. But when the carboxylic acid reacts with the alcohol, the product is a covalent compound. That's what we've just done over there. When that one reacts with that one, this thing that I have over here, let's take away all of that and that. This thing, let's go circle it with black. There we go. That whole thing is a covalent compound. Well, it's just covalent bonds that don't have any ions there. Yeah. Okay, do you understand what that sentence means? That's what I'm trying to explain to you. I'll read it again. They say, esters are common in, third paragraph. We can compare the reaction of ethanoic acid with an alkali. That was the reaction with sodium hydroxide. And with alcohol. That's this one. If we look at the equations, they are very similar, but the big difference between them is that the reaction with the alkali is ionic. All right? This one, this screen. There. The reaction here is ionic because it's an acid-base reaction. Acids are proton donors. There. And bases are proton acceptors. All right, so I get a salt there and water. All right, and then they say, and the reaction with alcohol is covalent. There we've got that. This product over here, these are all covalent bonds. I've not had an ion anywhere involved in the reaction. Okay. All right. And then we call this type of a reaction a condensation reaction. All right. Now, just the next section in your textbooks, there on page 140. We've already done isomers, so this is still ordinary level work as well. Just take a look at propane 1-ol and propane 2-ol. And then there on the right-hand side of the page, they just show the structures of some of the isomers of the compounds we've worked with. We've done them all. Okay. All right, then. The next part, big organic molecules. What's another word for a big organic molecule? Oh, a macromolecule. And macromolecules are giant covalent and polymers. So macromolecules, we get giant covalent. That's altyd hoop. Okay, people, macromolecules, we get the giant covalent structures. This would be things like silicon dioxide, graphite, and diamonds. All right? Now, yes, polymers. Oh, polythene, nylon. Okay, we get various polymers. We'll have a look at them in a moment. Okay. So, the big organic molecules are, in this case, that we are now interested in is the polymers. And we are going to go and look at proteins, fats, and carbohydrates. Okay, and we will have a look at how do we recognize each one of them. All right. So, in your books, they now start off with synthetic polymers. Now, I will do them in a moment. I just want to hand out when we start doing the condensation polymerization and when we start doing the nucleophilic substitution. So we are more or less at the part where you stop. Okay. Now, just take one of these, the higher levels. The ordinary levels, I think you can start summarizing. Yeah, basically. Yeah. Just let me have a look at something. Oh, resume. All right. Okay, grade 10s, 11s, 12s. The next section that we have to do has got to do with polymerization. Okay? Now, the polymers that we are going to have a look at are fats, proteins, and carbohydrates. Now, we have already done the formation of polythene. Bear with me. Okay, we said if we take ethene and we break the double bond, let me get the small rubber. We break the double bond, a bonding place opens up on either side, okay, and I can make this molecule stick onto itself up into infinity. No, you don't. You just show the bond opens up, and that is the repeating monomer building block. All right? Yes. Okay. If my monomer was this, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, hydrogen. 1, 2, 3. Hydrogen, 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 and hydrogen. 1, 2, 3, 4. Okay. What would this polymer look like? The repeating unit. What happens is, sorry, there mustn't be a hydrogen. We've got one too many. Okay? What is going to happen is, this double bond is going to be broken, and one bonding place will open there and there. The repeating unit is that. Yeah, it goes together with it. We are going to have something that's going to look like that. Yes. Can you see it? All right. The part where the one joins onto the other is where the double bond has broken. It's just very difficult if I wrote this compound like this and I asked you to do the polymerization of that one. Yeah, well, but it's difficult to draw it. So what I simply did was I bent this one down there. It's still just exactly the same compound. The double bond opens up either side, and this whole thing is the building block, the repeating monomer. Okay. Yes. Yes. No, technically not in terms of the one that looked like that. It's the same thing. Okay. Yes. Because it's just easier to see if you can put the double bond sort of alone on the molecule. No? Okay. But be careful, don't change the structure. All right. So that was just normal addition polymerization. All right. Now, in the next section, what we are going to have a look at is condensation polymerization. Now, we've done condensation when we did the formation of the ester, because when the alcohol and the carboxylic acid react with each other, it forms the ester plus water. So it's a condensation reaction, because we get the formation of water or a water-like molecule. Okay? Now, we are going to have a look at the polymerization or the structure of the molecules. Now, if you look on this handout that I've given you here, it's sort of typed and written on. We say macromolecules are large molecules built up out of similar units, the monomers or the building blocks. What are the building blocks of proteins? Amino acids, yes, okay. Now, we are going to have a look at structures called proteins, how they are formed. Protein. What are carbohydrates? Or sugars? Yes, it's a disaccharide, monosaccharide, okay. So we are going to have a look at, carbohydrates. And lastly, we are going to have a look at fats, which are actually esters. The alcohol plus the carboxylic acid forms the ester. Does it fit? Yeah. Okay. Now you will see on the note that I've given you, then next to, we are going to have a look at synthetic polymers and at natural polymers. Protein is a natural polymer. Nylon is very similar to protein. It's just synthetic. Okay? Then we are going to have a look at polyester. It's an ester, which is a fat. Your shirt is made from polyester. Yes? Okay. And then normal fats from plants, oils, etc. Just basically the structures of that. And then lastly, the carbohydrates, which are made by sugar units that are joined onto each other by means of condensation polymerization. All right. Now, a protein molecule can be recognized. It's a hydrocarbon molecule like that. But on the one end, we have nitrogen, and on the other end, we have a carboxylic acid group. This is a building block of proteins. How do we recognize a protein? Specifically, nitrogen, hydrogen, hydrogen. When one building block, one monomer, bonds onto another one, we find that my second molecule, let's clone this one. See if it'll clone. No, it doesn't want to go. I must go over there. Let me first go undo Okay, I'm there. Let's see if I can get it to go. No, doesn't want to do it. Okay. Let me just undo the shake. Doesn't undo the shake. Yeah, but I want the whole thing. It's not going to go. Not that I know of. No, doesn't want to do it. Okay, it doesn't matter. We will have, let's draw the one. Nitrogen, hydrogen, hydrogen. We have hydrogen there, and oxygen, OH there, and doesn't matter. I've just taken a different molecule, okay? So I am going to make a condensation reaction, and what happens is, let's see if this thing would go. Yes, I want to clone it. Clone there. And now I want to turn it upside down. No, I don't. I want it like this. Okay. And we are going to get okay. I've turned this molecule upside down. All right. Now, what is going to happen is we are going to get, well, there. So we are going to end up with carbon, oxygen, carbon, oxygen, and then carbon, nitrogen, nitrogen. No. No. Okay, sorry people. We are going to, I need to turn this one back. Like that. There. And what is going to happen is this hydroxyl group and one of those hydrogens, they are going to form water. So we are going to end up with, I'm not going to draw that whole structure, carbon, nitrogen, hydrogen, okay, and then carbon, double bond oxygen, carbon. Okay, nitrogen, hydrogen, oh. Hydrogen. Yes. Okay. Plus water. Let me redo it on a clean screen. Okay. Now, we don't need to know the specific number of carbons in the molecule, the specific form of the molecule. We replace that with a shape. So we don't need to know the specific chemistry of a specific amino acid. I will say I have an amino acid. There is my nitrogen, hydrogen. Okay, and on the other end of my amino acid, we have the carboxylic acid group over there. Okay, so if I have another, let's do it in a different color, amino acid, all right, and we have the double bond oxygen OH over there, and here we have the nitrogen, hydrogen over there. Now, yes. Oh, the oxygen is stuck onto the carbon. Yes. All right. Now, we are going to get a condensation reaction there. So what is our molecule going to look like? Nitrogen, hydrogen, all right? And now, carbon, double bond oxygen, and there is the other rest of the molecule. Okay, that is the formation of a protein. Now, this part over here, that is known as an amide link. All right. Okay, it's just that there. It's just, yes, yes. Okay, as it is over there. All right. So then the next one can add on and the next one can add on. Yes. Yeah, it splits out a water molecule. That's why it's condensation polymerization. Now this would be normal protein molecules. Now when we make synthetic protein molecules, for example nylon, instead of having our building block a carboxyl group and the nitrogen-hydrogen group on it, we have a diamine reacting with a dicarboxylic acid. I'll show you. Now, a diamine is going to look like that. There is going to react, with a dicarboxylic acid. Carbon double bond oxygen. Oh, you do? Carbon double bond oxygen, but it's exactly the same. OH over there. So now we have a diamine and a dicarboxylic acid because it's got the functional group on either side. They do this so that the molecule can grow simultaneously in both directions. It's just faster when you start making them synthetically. So now where's the reaction going to lie? Condensation is going to occur there. So what will my resulting molecule look like? There, that part is the same. Nitrogen, hydrogen, and now onto the carbon double bond oxygen, and there goes the rest of the molecule. And what do we have? Plus water. It is a condensation polymerization reaction. Yes. So this is natural proteins will look like that. On the one end is the carboxylic acid group, on the other side is the amide group. But they still react the one onto the other by means of condensation polymerization. So this would be the natural one, and this would be the synthetic one. They can go to both sides. Okay. Now, yeah, well, then it will stop. Then your reagents have been used up. One molecule is not going to... Yeah. But they will work it out to add equivalent volumes to make it react like it should. Okay, now, people, this is condensation polymerization. The opposite of condensation polymerization is the breaking up of a molecule using water. We call that hydrolysis. How's it going to break when I add water to it? It's going to break over there, a hydrogen will go there, and a hydroxide will go there. Do you understand that? Hydrolysis. It's going to look, we're going to end up with a molecule that looks like that and like that. Do you understand? All right. Yes. Why must you chew your food carefully? Yeah, the saliva helps with the breaking down of the starches, but by means of hydrolysis. Yes. All right. Are you with me? Sien jou kop werk. Okay. I'll show you. Okay. Just can rub that out. Let me extend the board. In other words, it's going to break over. Yeah. I'm going to add in water. So what is going to happen? Let me just take that one out there. All right. We are going to have that the nitrogen and the original hydrogen. Okay, but now there's a bonding place open over here because I've broken the bond. And on that molecule, there, I have carbon double bond oxygen, and I have a bonding place open there, but I have got water, which I could write as HOH, all right? Let's write it as H. Just want to take that away. All right, as H and OH. So I can take that hydrogen, it's going to go there, and I can take that, oh, now I must turn it upside down. Why must I turn it upside down? Because it bonds onto the oxygen. Do you understand that? Okay, so this is condensation polymerization, and that is hydrolysis. Okay, hydrolysis is the breaking up of a long molecule or of a molecule by adding water. All right. It's got to do, it's actually not that simple, the answer, but why doesn't it break on another point? It's got to do with the reaction of the nitrogen, which is much more, is the electronegative. It's more electronegative than carbon. And hydrogen is totally less electronegative, and then there's attractive forces between them. Okay. You would need probably a bit of heat. I don't think it would just happen without a catalyst. Also, you can chew your food. If there isn't an enzyme, you can't break down the starch. Okay, so there will be temperature, catalyst, pressure will play a role. Okay, we don't go into it once again. If you go and do organic chemistry, then you will go and do all those finer details. All right, now, I want to have a look at the next one. Yes? The natural one, there. How would hydrolysis of that one look like? Exactly the same. I would have my nitrogen and the hydrogen. There's a bonding place that opens up. And over here, I have my carboxylic acid. And I have a carbon double bond oxygen and a bonding place that opens up there. And here goes my water. Let's go H. OH, see if it'll go separate. Now it doesn't want to go separate. H and there, OH. Okay, there it'll go. I must make it upside down because it must bond on the oxygen there, and that one will bond on the hydrogen. And there we have hydrolysis of the molecule. Okay. Okay, now I want to do carbohydrates. Now once again, we aren't interested in the specific structure of the sugar molecule. Only 4 minutes. Then we're finished. All right, sugar molecules, well, we'll just draw them like that. Okay? Say again? Yes. And okay, you've done them in biology, haven't you? What would hydrolysis of this carbohydrate look like? I'm going to break it. There. All right. So we will end up with, there's our oxygen. I'm breaking it over there. Here's my other molecule. There. Now, on the corners, this is where the carbons are. Okay, I think there's an oxygen over there and a carbon there, if I remember correctly. But you don't need to put them in. But on each carbon, there is a hydrogen and an hydroxide, if I have them separate. So all that happens is, onto that one will go a hydrogen, and onto that one will go the hydroxide. On each carbon there's a hydrogen and a hydroxide. Yeah. But you don't need to draw it. You don't need to draw it, eh? You can just draw a shape. Okay. So here we have carbon, oxygen, carbon. All right. So it's going to break over here either on that side or on that side. It doesn't matter. All right. So it has. I've broken it over here on the green line. All right. There. So that one takes the oxygen, so it gets a hydrogen, and that carbon gets the hydroxide. Okay. How would the condensation polymerization of simple sugars look like? Well, I'll have a sugar molecule. On that carbon will be a hydroxide and a hydrogen. I will have another sugar molecule like that, and on that carbon will be a hydroxide and a hydrogen. What will happen during condensation polymerization? Yes. And doesn't matter. What will we get there? Oxygen and there. Say again? Yes. Yeah. Yeah. Nothing else. Are you with me? That is for the carbohydrate. Okay. And then a polyester has got the ester link, and once again, the alcohol and the ester, we work with a dialcohol and a dicarboxylic acid to form the ester. I'll show you. We have an alcohol. Yeah, well now I'm going to do the ester. Yes, so ester molecule, the building block. So we will have carbon, double bond oxygen. This is the carboxylic acid, sorry, hydroxide. Okay. Over here, carbon, double bond oxygen, hydroxide. And I am going to make it react with an alcohol. So we have carbon OH and 1, 2, 3, 4 hydrogen, hydrogen. Okay? Where's it going to go? Yeah, the side is also going to have the carbon. Sorry, let me just do it quickly in red. It's going to have, the hydroxyl group there. I don't want to draw the carbon in there. It just confuses you. Yes. So there we have OH. Now, where's the condensation reaction going to occur? Doesn't really matter which one goes where, does it? Okay, because what is the molecule going to look like there? Carbon, double bond oxygen, oxygen, there, OH. Are you with me? This thing over here is called an ester link. Carbon, double bond oxygen, oxygen is the ester link. How am I going to break it by hydrolysis? Where will it break? Yes, there. Okay. Where will it break? It's not going to matter. Because you are going to end up with a carboxylic acid and an alcohol. All right. Okay, that's it.